Definition 17.2 is going to finally give us the definition for the inverse function. Now I want you to notice that it starts with saying let f be a one-to-one function. So it's not possible for us to be able to create an inverse function without first having a one-to-one function to go with it. So if you go back and look at the previous example, that would have been example 17.2, both f and g, which were the cube root function and the cubic function, those both passed the horizontal line test. Those are both one-to-one function. And as it turns out, they are going to fit the condition for being inverse functions. So let's go further into this definition. It says the domain of f is going to be A, and the range of f is going to be B. So in other words, we could do a mapping that would say f colon, and then we could say A ends up mapping over to B. That's what that's saying. Now, it then says the inverse function of f, which is going to be denoted with this notation here, f with a superscript -1. Definitely good for us to mention here that this -1 is not an exponent. It is a superscript, just like you can have superscript on a word processor like Microsoft Word, but it is not to be considered an exponent because you're putting that superscript on a function name, not on a number. It's on a function name. So that is purely just there to talk about the inverse of function f. So what this means is that the function is defined to be f inverse of y is equal to x if and only if f of x is equal to y. So what we're used to saying is that f of x is always the same as talking about the y value. Well, now when we talk about the inverse, they're saying that the inverse is actually talking about x values and that you're going to input y values into it. So what this is claiming is that we're going to be switching the role of the x and the y. So that's what my second note here talks about. It says the role of x and y becomes switched. Now the first note says that that means that the domain of f inverse is going to be B and the range of f inverse is going to be A. So if I wanted to write that using some mapping notation, I would say f inverse is going to be going from B to A. So notice that that is going to be the exact opposite of what we had up here for f. So all the x values now become y values, all the y values now become the x values. So we're switching the role of x and y. So to help us get a better understanding for this, I want to look at a finite map or a finite function here with example 17.3. So it says here let f equal, and then we have 1, 2, 3, 4, 5 ordered pairs. So this is definitely a finite map. It's only 5 ordered pair there. Then it says to create an arrow mapping diagram for f, and then the same for f inverse. Now we know that we are only supposed to do this if our function is a one-to-one function. So let's verify all of that with the arrow map. The arrow map hasn't been done since early in the semester, so let me remind us of how to do that. We're going to make 2 spaces. The space on the left is the first set. That's going to be the domain. So looking at all the x values or all the first entries of your ordered pair, we will list -2, -1, 3, 5, and 6. And then the second set is going to be where we put all the range values. This will be 4, 1, 0, -4, and 7. And then we're supposed to make a connection with the arrow mapping to show how the different x's correspond to their y. -2 maps to 4, -1 maps to 1, 3 maps to 0, 5 maps to -4, and then 6 maps to 7. And we'll name this f. And this is exactly what we want to see, because every x value goes to only one y value, and none of the y values ever get used more than once. This is a one-to-one function. So let's go ahead and make the inverse map for this. And we will call the inverse map f inverse, because I'm not just going to create a completely new function from scratch. I'm going to use what I already have. So I'm going to take the range values and I'm going to put them as the domain values now, taking the y's, making them the x's. Then I take the domain from f and I turn it into the range for y, or range for f inverse. So -2, -1, 3, 5, and 6 go into the second set. But when you make a map, you're always connecting x values to y values. So now 4 maps to -2, 1 maps to -1, 0 maps to 3, -4 maps to 5, and 7 maps to 6. So all we're doing is just switching the order of the ordered pairs. So to define f inverse using set notation, I'll say f inverse equals, and then I'll literally write down all the ordered pair. 4, -2, 1, -1, 0, 3, -4, 5, and 7, 6. So as far as the definition is concerned for the inverse function, it's a very simple definition. All you have to do is switch the x's and the y's. But there's so many interesting things that happen when you do that and then start comparing the function that you started with to the inverse function, as we saw with example, what was that, 17.2, where we saw the line of reflection, we saw the opposite operations in the reverse order, and then we saw the compositions and what they did. So very interesting things that happen when we create these maps using a inverse relationship.